Welcome to Encryption Fundamentals. In this video, we'll explore how encryption protects your data. Encryption is the process of transforming readable data, called plain text, into an unreadable format known as ciphertext. This ensures that even if someone intercepts your data, they can't understand it without the correct key. Let's explore the core concepts of encryption. Algorithms are like recipes for scrambling and unscrambling data. Keys are the secret ingredients needed to make the algorithm work. Without the correct key, the data remains scrambled. Symmetric encryption uses a single key for both encryption and decryption. Think of it as a shared secret code. The sender uses the key to encrypt the plaintext message, turning it into ciphertext. The receiver then uses the same key to decrypt the ciphertext back into the original plaintext. Examples of symmetric encryption include AES, the Advanced Encryption Standard, and Blowfish. Asymmetric encryption uses a pair of keys, a public key for encryption and a private key for decryption. The public key can be freely shared, while the private key is kept secret. These keys are mathematically related but practically impossible to derive from each other. The sender uses the receiver's public key to encrypt the message. Once encrypted, only the receiver's private key can decrypt it. RSA, which stands for Rives Shamir Adleman, and ECC, or elliptic curve cryptography, are examples of asymmetric encryption. Let's compare symmetric and asymmetric encryption to understand their different strengths and uses. Symmetric encryption uses a single shared key, while asymmetric uses a key pair. Symmetric encryption is faster but requires secure key exchange. Asymmetric encryption offers stronger security and is ideal for key exchange and digital signatures, while symmetric is better for encrypting large amounts of data. Hashing creates a unique fingerprint of your data to ensure its integrity. This means verifying the data hasn't been tampered with. Hashing is a one-way process. You can't reverse engineer the original data from the hash. A small change in the input creates a completely different hash output, making it ideal for detecting even tiny alterations. Let's recap the fundamentals of encryption. We've covered how encryption transforms plain text to ciphertext, the role of algorithms and keys, symmetric and asymmetric encryption approaches, and hashing for data integrity. Understanding these encryption fundamentals is essential for appreciating how our digital communications and data remain secure in an increasingly connected world. Welcome to our exploration of encryption today and its future. We'll look at current trends, threats, and how encryption continues to evolve. A major challenge to modern encryption is quantum computing. While classical computers would take billions of years to break RSA encryption, quantum computers could potentially do it in hours. To address this threat, researchers are developing quantum-resistant algorithms. The National Institute of Standards and Technology, or NIST, is leading this effort. NIST has selected several algorithms as standards for post-quantum cryptography, including Crystal's Kyber for encryption and Crystal's Dilithium, Falcon, and Sphinx Plus for digital signatures. Homomorphic encryption is another exciting development. It allows computations to be performed on encrypted data without decrypting it first. This means sensitive data can remain encrypted while being processed in the cloud, opening new possibilities for secure cloud computing and data analysis. Artificial intelligence and machine learning are being integrated into cybersecurity systems to enhance threat detection and response. These systems can identify anomalies, recognize patterns, predict threats, and even automate responses to attacks, significantly improving security posture. Cyber resilience is becoming increasingly important. It's the ability to prepare for, respond to, and recover from cyber attacks. A comprehensive resilience strategy involves 5 key components: identify, protect, detect, respond, and recover, forming a continuous cycle. With the proliferation of Internet of Things devices, securing these devices with robust encryption is becoming critical. IoT devices present unique security challenges due to their limited processing power, diverse ecosystem, inconsistent updates, and physical access risks. In response to these challenges, the U.S. government has issued National Security Memorandum 10, which sets requirements for migrating to quantum-resistant cryptography. The timeline includes completing inventories by 2025, implementing plans by 2027, migrating critical systems by 2030, and achieving full migration to post quantum cryptography by 2035. As we've seen, encryption is constantly evolving to address new threats and technologies. Staying current with these developments is essential for maintaining robust security.